like that. So whenever we sample it, the amplitude is changing. So if I take the impulses, right? So if the impulses at that impulse T1, T2, T3, T4, T5, this is like that. So at T1 we get this impulse. We have to hold this amplitude to process. Otherwise, this T2 will come. So before we coding, they get the coding. So that's why we need the whole circuit as well. So this is the block diagram. So here we can see here a sample and whole circuit. We give the input analog signal. Then there is also a clock signal so that it will generate the clock interval, and then it will give you an analog signal segment. And then after that, we will give it to the analog to digital conversion. Then we will get our equally spaced digital signal. Or we can have also this kind of circuit. This is the same block diagram. So we have a sampler circuit. In the sampler circuit, we have this low pass filter circuit, and then we'll sample it. Then we'll have the holding circuit. I'll show you what is the holding circuit, and then we'll talk about this quantizer and encoder. So this is the overall analog to digital ADC block diagram: sampler, holding circuit, quantizer, and encoder. A sample and hold circuit sometimes represent as SH circuit or SNH circuit. Sample and hold or SH. And is usually analog to digital converter to sample input signal and hold the sample signal. In SH circuit, the analog signal is sampled for a short interval of time. Usually it takes only 10 microseconds to 1 microsecond. And after this sample value is held until the arrival of the next input signal to be sampled. And duration of this holding, the sample will be usually between few milliseconds to few seconds. This is the time frame. And this is the hold circuit. In the hold circuit, we will have a capacitor, as I mentioned, and a mechanical switch. So during this holding, whenever once the sample is done, then this switch is connected to the whole circuit, and we hold that amplitude of the sample interval, so that we can get the conversion, the quantization, the encoder will be done. Once it will be done, then this switch will come back again to here. Then the next pulse will go to for the circuit. So this is the holding capacitor and analog switch. With these two components, we can design our whole circuit. So in this holding circuit, we can reduction of the continuous signal to a discrete signal, right? We are getting actually from a continuous signal to a discrete signal. In our last lecture, we already saw that a CTS and DTS. The sampling means a conversion from a continuous time signal to a discrete time signal. In the discrete time signal and the continuous time signal, in the continuous time signal, both the time and the amplitude is continuous. In the discrete time signal, the time is discrete but amplitude is continuous. Then we'll get the conversion. Switch on means sampling of the signal, and switch off means voltage stored in the capacitor and must hold the sample value constant for digital conversion. This is another block diagram. So this is the block diagram from our reference book. You can see this kind of block diagram of the circuit, the simple one. So in the sampling theorem, what we found that the sampling frequency must be greater than or equals to maximum frequency component. Maximum frequency component. Otherwise, aliasing will take place. That means an interference will take place. That's why we have to have a low pass filter. We have to have a low pass filter. At first, we have to have a low pass filter to get a band limited signal. We cannot process an infinite signal. So we need to make a band limited signal. To get a band limited signal, we pass it to a low pass filter. It is also known as anti-aliasing filter. An anti-aliasing filter and a sample hold circuit are two functions typically found in the digital signal processing system. Sample and hold function does two operations. The first option is sampling, that we already discussed. And what is sampling? Sampling is the process taking a sufficient number of discrete values at points on a waveform that will define the shape of the waveform. So if you take more samples, then it will define more of your input signal, right? If you take, for example, this one. So this is our signal. So if you take only 2 samples, it will not define whole your signal. But if you take more samples, it will define your waveform more precisely. So sampling is the process of taking a sufficient number of discrete values, at points on a waveform that will define the shape of the waveform. The more samples you take, the more accurately you can define the waveform. Sampling converts an analog to signal into a series of impulses, each represent the amplitude of the signal at a given instant of time. So as I mentioned, whenever we get these things from the computer, so that means now we are getting some impulses. So these impulses will give you some amplitude. Series of impulses, each represent amplitude of the signal at a given instant of time. T1, T2, T3. So we have some amplitude, a constant amplitude. Okay. So what is the sampling theorem finally? The definition, the sampling theorem states that in order to represent an analog signal, the sampling frequency must be at least twice the highest frequency component of the analog instrument. So this is the definition of our sampling theorem. Another way to say that the highest analog frequency can be no greater than 1 of the sampling frequency. So this, if we don't use the low pass filter, aliasing will take place, then we lost some of our information. Okay. And when we got another one is the Nyquist theorem, right? The Nyquist theorem is the minimum frequency. The minimum frequency Ws should be equals to twice of Fn. So low pass anti-aliasing filter must be used to limit the frequency spectrum of the analog signal for a given sample frequency. And to avoid this aliasing error, the filter must be at least eliminate all analog frequencies above the minimum frequency in the sampling spectrum as illustrated in the figure. Okay, now we'll go for the quantization. That means we have to give some values of the amplitude that we already sampled, right? We already sampled here. So quantization, a continuous signal such as voice has a continuous range of amplitude. Therefore, its samples have continuous amplitude range. But it is not necessary. It is important. It is not necessary to transmit the exact amplitude of the samples. Why? Because it's a human nature. I think you can you read? Easily? But they are not, the letters are not in order, right? But we can read. The technique is the first of the word, the first letter and the last letter should be fixed. So that if you just change, our memory, our brain can detect. We can read easily. Same thing, we can also hear if the amplitude, if you don't even send all the exact value, even that we can, whenever we get the signal on the other side, we can actually hear what actually we are trying to hear. So we can set this sentence as that. So it is not necessary to transmit the exact amplitude of the samples because any human cells work as ultimate receiver. It is known as ultimate receiver. Your eye or your ear is.
I have a question.
Yeah.
So, the question is, first and the last, we keep it same, but our senses get, okay, this is the word or this is the sound.
Because we already know what this word, that means whenever, how are you? So we know how are you, H-O-W or H-W-O, but your brain will read actually how.
But an electronic device cannot understand that thing.
No, I'm not talking about the device, I'm not talking about the samples, I'm talking about the human sense. So
okay.
That means you don't need to send the exact amplitude. It's not like that because we have pulses, right? This is a continuous, it is from 0.00002 to 0.1111, right? So you don't need to send exact amplitude. Even that you can actually, whenever it will be sampled, we can actually make the single signal again as it is. So it is like a hypothesis. You can call it a hypothesis. Okay. So this means that the original continuous signal may be approximated. The original continuous signal may be approximated by a signal constructed of discrete amplitude, selected on a minimum error basis from an available set. Okay. So now we'll go for the quantization. So I will come to this slide. Now I will try to use this board, then I will come to slide again. So we can say that amplitude quantization. Now we are talking about this amplitude, right? Here in the signal, we are trying to quantize the amplitude. So amplitude quantization is defined as the process of transforming the sample amplitude. If I write down, this is M and Ts. This is the sample amplitude. Of a message signal MT, into discrete time amplitude signal, discrete amplitude signal, we can say this is Mg and of Ts at time t equals to nTs. So you already see that this is the sample. So we are trying to transform this message signal MT into a discrete continuous signal, right? Decreased amplitude signal. This quantization can be uniform or non-uniform. I will upload this hand. This quantization can be uniform or it can be non-uniform. If it is uniform, it means the representation levels are uniformly spaced. The representation levels will be uniformly spaced. So usually we discuss here about this uniform quantization where the representation levels are equally spaced. This quantization characteristics can be two types. One is known as mid-trade. Another is known as mid-rise. This quantization, uniform quantization. There are two different kinds of quantization. One is uniform and is non-uniform. We are talking about the uniform quantization. This uniform quantization have mid-trade and mid-rise. What is mid-trade? A mid-trade quantizer is a type of uniform quantizer that rounds value to a finite set of uniform output levels, including 0. That means this is my input level and this is my output level. Okay? So whenever the signal will pass, it will, whenever it gets to 0, it passes through 0. It passes through 0. I'm talking about mid-trade. Then it will go, whenever it gets 0, it passes through. Whenever it passes through. Like this. So it actually also take the level of 0. Okay. So this is called mid-trade. A mid-trade quantizer is a type of uniform quantizer that rounds values to a finite set of output level, including 0. It will get the including 0. It is useful when it's important accurately represent the 0. An example of this one in audio coding and control system. Audio coding and control system. On the other hand, the mid-rise, in case of mid-rise, a mid-rise quantizer is a type of uniform quantizer that maps input values to a finite set of output values. It is used in our digital communication and signal processing. That means in our case, we actually focus on mid-rise. So mid-rise means whenever it will get the interval, it will rise. So whenever it will come to here, reach to 0, so it will get to rise. So at T1, it will rise. Then at T2, it will get again rise. At T3, it will again rise. So it will rise at the interval. Okay? So the mid-rise quantization creates a symmetric distribution of the quantization level. So if you go from here also, like this. So it will be more clear maybe with one example, that it will be hopefully more clear. So quantization process, how we can quantize the sample signals. We already have the sample signals, now we have to quantize them. For the quantization process, the first step, total dynamic range. Total dynamic range, your input signal. So we already have our input signal. So this is our for example, this is our input signal. And this input signal have dynamic range from 0 volt to, for example, 8 volt. So the first step, total dynamic range of the signal is divided into L equal number of steps. L equal number of steps. Right, L equals to 2 to the power n. This is also known as quantization level. This L is also known as quantization level. And here n is the number of bits. Because we are trying to convert from analog to digital. That means you want to represent each interval with some code, right? And that code is depends on 0 or 1, either 0 or 1. That means number of bits. So if you increase the number of bits, then it will give you more higher resolution. We'll see. So the first step of the quantization process, total dynamic range of the input signal should be divided into some quantization level L, and where L equals to 2 to the power n. And here in this equation, this n equals to number of bits. The second step, middle of each step will be selected at quantization level. Middle of each step will be selected at quantization level. So if I draw, let me draw here, L equals to 2 to the power n. Okay. So for example, this is 1. Then we consider n equals to 2. So if n equals to 2, 2 to the power 2 means 4. And here it is, we have 0 to 8 volt. So we have to divide this whole range of the dynamic range into 4 levels, right? So maybe 2 volt, 4 volt, 6 volt, and 8 volt. Then the second step, middle of each step will be considered or selected at quantization level. So that means this 1 volt is my quantization voltage. This 3 volt is my quantization voltage. This 5 volt is my quantization voltage. This 7 volt is my quantization voltage. At first we need to take the dynamic range. We have to, depending on the number of bits, we can divide them. So at first we start with the very minimum one, that we think that n equals to 2. Okay? So n equals to 2 means we have 4 different levels. 0 to 2, 2 to 4, 4 to 6, 6 to 8. Okay. Then third one, each of voltage corresponding to a step will be rounded off to a middle of the step, or each of the sample will be rounded off to one of the nearest quantization level. So here we can sample it, right? This one we can be sampled. We can sample it. So we have T1, so it is sampled here, T2 sampled here, T3 sampled here, T4 sampled here, T5 sample here, T6 sample here, T7 sample here, for example. Can you see? So we have the sample now. So what we can do now? We can see in this quantization process, we will not getting the exact amplitude of the signal. So that means there will be some gap, and that gap is known as quantization error. So we'll see how the quantization error will be here. So for this level, we have another equation is known as step size or the resolution. This step size equation is V max minus V min divided by 2 to the power n. V max your maximum input voltage, V min is your minimum input voltage, and 2 to the power n is your quantization level. So here in this case it is 8 minus 0 2 to the power 2, right? 8 divided by 4 equals to 2. So step size is 2. 0 to 2, 2 to 4, 4 to 6, 6 to 8. Then the quantization voltage will be in the middle of each step. It is 1 volt, 3 volt, 5 volt, 7 volt. Now the third step, what they said, that your value, your sample value will be rounded off to the nearest quantization voltage. To the nearest quantization voltage. So if we see one example, it will be clear. If we see one example, for example, our quantization voltage is given. So we have the sample voltage, we have quantization voltage, then we can say coding, encoder, and we can see the quantization error. So as you are trying to get from analog to digital converter, and we are having these two step size is 2, where 2 to the power n equals to 4. So 4 steps means we can name them. This one as 0, 0. Zero, 1, 1, 0, 1, 1. Okay. So now for example, just for example, we have time interval, we have sample, and the sample voltage are 0.6 volt, 1.7 volt, 2.2 volt, 0 volt, and 8 volt. Okay. So we already have this sample from the sampling circuit. We have the sample voltage, and we have already know what is the quantization voltage. The third step is we need to round off to the nearest one. Okay. So when it is 0.6, we can see 0.6 maybe nearest is 1 volt or 3 volt. So nearest 1 volt. So it will be 1 volt. And this 1 volt corresponding to 0, 0. Then for 1.7, so 1.7 may be here. So 1.7, which one is close, nearest? Is 1 volt or 3 volt? 1 volt is near. So still it will show, though we have a sample value of 1.7 volt, but we are getting quantization of 1 volt. And this 1 volt again 0, 0. The third sample value is 2.2 volt. So now 2.2 volt, we can see that 2.2 volt is close to 3 volt. Because it is 8 volt, and if you go for 1 volt, it will be 1.2. So it is nearest to the 3 volt. So the quantization voltage is 3 volt. And this quantization 3 volt is corresponding to 0, 1. Then 0 volt. 0 volt, of course, goes to 1 volt. And it is 0, 0. And 8 volt is corresponding to 7 volt. 7 volt, it is 1 volt. From this table, obviously, we can see there are a huge gap. It's a huge gap. So we can easily calculate this error. So this quantization error is, the equation is sample voltage subtract quantization voltage. So 0.6 to 1 minus 0.4 volt. Here 1.7 to 1.7 volt. Here 2.2 to 3. So minus 8 volt. Here in this case we have minus 1 volt. Here in this we have plus 1 volt. From the table we can also see that what is the maximum error? Maximum error is 1 volt. So maximum quantization error is having 1 volt. So maximum quantization error, we can say it is step size over 2. You can see the step size is 2 and we have maximum error is 1 plus minus 1. So this is the maximum error. Now if you just increase your resolution, number of bits, for the same example, now if you consider n equals to 3, so it will be 8, right? Then step size will be 1. Step size will be 1. So if the step size is 1, what will happen now? So we will have how many stages? Zero, 1, 2, 3, 4, 5, 6, 7. Right? 0 to 7, 8 volt. Because now step size is 8, 1 volt each. Right? That will have 8 steps. And the quantization voltage will be now 0.5, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5. Okay. So now if you go to the same example, now this 0, 6 is close to what?
0.5.
0.5. 0.5. 1.7 close to 1.5. 2.2 close to
2.
2. 0 close to 0.5. 8 close to 7.5. So this 0.5 corresponding to what? 0, 0. So you put, now we have 3 digits, right? So it will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So if I put the value here, so 0.5 corresponding to what? 0, 0, 0, right? 0, 0, 0. 1.5 corresponding to 0, 0, 1, right? 2 volt corresponding to, sorry, 0, 0, 1. 0.5 corresponding to 0, 0, 0. 7.5 corresponding to 1, 1.
We should have 8 also. 0 to 0, 0, 0, it comes on as 0.
So if I choose this one, right?
Yeah.
Sorry, if I take this as 0, 0, 0, then you'll be fine, right?
That's enough.
Huh?
The quantization voltage, not the, it should be the 0.5, 1.5, not the.
Yeah, 0.5, 1.5, 2.5.
Yeah.
Yeah.
But 7.5 should be a
7.5
quantization.
also. We should have 7.
Okay. Yeah.
But I have a question.
Okay, one minute. I'm coming. At first I take this one. Did I make any mistake? 0.5.
Oh,
Yeah. So we should have 8 volt until 8 volt.
Yeah.
Yeah, thank you. No, it's fine. Yeah.
And it's 2.5 quantization value, so
0.5, 1.5, 2.5.
in the box.
2.2.
So
It comes
2.2.
under 2.5.
Oh. This one, right?
Yes.
But it's close
Yeah.
to the
No, I'm coming to you.
Alright.
Yeah.
2.5.
So 2.2,
It's close to 2.
I think it's 2, not 2.5.
We'll check the
2.5 is not
quantization.
option.
Quantization.
Oh, quantization, yeah. Quantization is 2.5.
Oh,
Yeah.
well,
Because whenever you start here, 1.5 and 2.5. So it is
Oh.
close to 2.5. Yes.
And the same thing is.
So now it's fine, everything? 0.5, 1.5, 2.5, 0.5, 7.5. Now if you see here, the error become how much? 0.1. It is 0.2. It is 0.3. And this is the maximum 0.5. This is also 0.5. So we can reduce the quantization error. So if you increase the number of bits, we can reduce the quantization error. So now if you make it 2 to the power 4, it will be 16 steps. So now it will comes to 0.25. It will come to 0.25. Okay. It is very short lecture. So this is the quantization. The process of converting an analog value to a code is called quantization. So we are just converting this analog value to some code. Okay. So quantization and encoding is together. Quantization and encoding, we can say, is together. So whenever we'll see the next week, we'll see about talking about this circuit, different kind of circuit for this conversion. Then we'll get the code exactly. So, but before that, we have to have some quantization value. So during the quantization process, the ADC converts each sample value of the analog signal to a binary code. The more bits that are used to represent a sample value, the more accurate is the representation. That we already saw. So to illustrate, like what does reproduction of the analog waveform into 4 levels. I will show you. This is the example from our reference book. This is the same thing. So at first we have just only 4 levels. So as it is 4 levels, 0, 1, 2, 3. That means 0, 0, 0, 1, 1, 0, 1, 1. They didn't mention about any voltage, okay? No dynamic range. And this is the signal. This is the signal and these are the impulses. So we have time interval, same timing interval. So we have from 13 sample intervals. So if you go for the first interval, it is what? 0, 0. For the second interval, it is 0, 1. For the third interval, it is 1, 0. For the fourth interval, it is 0, 1. 5 also 0, 1, 6, 0, 1, 7, 0, 1, 8 again, 1, 0. Then from 9, 10, 11, 12, 1, 1. So we can have the table like this. So the data is quantized to the next lower level as shown in the table. So these are the sample interval from 1 to 13, and these are the quantization level. And these are the binary code. So whenever you just send in the process, what we can send, we just send a serial binary bits. 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1. So it will get an idea what is the amplitude of the voltage. So now, if you look at here, if we take the lower bit, we cannot actually represent properly the signal. There will be some information will be missed out. Or we can say that whenever we reproduce the signal, we will not get the exact signal. So that's why we can have to increase the number of bits. So this was the number of bits. Now we have 2 to the power 4, that means 16 input combinations. Now from 0, 0, 0 to 1, 1, 1, 1. Now we can have same interval from 1 to 13, same interval. Now if you look at this table, we can see that we can quantization value of 16 different levels. Previously it was only 4 levels. Now we have 16 different levels, So we can more precisely represent our input waveform. Okay? So this is how we can get this information. So if in the Excel, maybe I'll give the picture, you have to find out this quantization level and accordingly equivalent code of the binary. So we can say that quantizing means breaking down analog value into a set of finite states. And encoding means assigning a digital word or number to each state and matching it to the input signal. So when an analog signal is to be sampled, there are certain criteria that must be met in order to accurately represent the original signal. All analog signal contains a spectrum of component frequencies, right? For a pure sine wave, these frequencies appear in multiple called harmonics. And these harmonics of an analog signal are sine wave of different frequencies and amplitude. If it is a multitone, so all are sine wave but in different harmonics. So when the harmonics of a given periodic waveform are added, the result is the original signal. So all will be given like this. So in the example, you have 0 to 10 volt, separate them into a set of discrete states with 1.25 increments. How we get this 1.25 increments? By using the same equation. Because you already know the number of possible states, we can determine that converter of the output is L equals to 2 to the power n or L equals to 2 to the power n. Here I just mentioned L, same quantization level. And where n is the number of bits in the analog to digital converter. So for example, a 3-bit analog to digital converter means 8. So we have given a dynamic range of 10 volt, right? Dynamic range of, in our previous example, dynamic range of 10 volt, 0 to 10, 0 to 10. So if you just divide this 0 to 10 volt by 8, we'll get 1.25 volt. That means each quantization level, each step size has 0 to 0.00 to 1.25. So we have to have quantization voltage in the middle. So anything in between that will be round off nearest to the quantization voltage. So we have that level from 0, 0 to 1.25, then 1.25 to 2.5, 2.5 to 3.75, 3.75 to 5. In this way, we have 8.75 to 10 volt. These are the step sizes, quantization. Then the quantization voltage will be in the middle. Then whatever the sample value, we need to round off nearest to the nearest quantization voltage. And then we can also calculate the quantization error.
Quantization, I mean, generally we do after the sampling.
Yes.
And
Because we'll give the intervals.
okay, so first when we give an analog signal, we'll encode it, sample it, quantization, decode it.
So this is the first we'll give to the sampler, analog signal to the sampler. In the sampler, it is also a whole circuit. So once we sample it, for example, this 1.6 volt, we sample it. That means this is your signal. This is the sample. For example, this is 0.6 at T1. So it will hold. Here we also have a whole circuit. In the whole circuit, then this 0.6 is given to the quantizer. Now quantizer will give some discrete voltage or amplitude of the signal. After that, it will give it to the encoder. Encoder will then give some equivalent digital bits. So this is equals. So here, before sampler, we have a signal which is continuous in time, continuous in amplitude. Here, before we have continuous but discrete in time, and after that, discrete in time and discrete in amplitude. Then we code it. Okay. So in the example, in the exercise or in your Excel, maybe it will be given like this. You have 0 to 10 volts, separate them into a set of discrete states with 1.25 volts or 0.625 volts. So you have to calculate accordingly. Okay. Then we can assign, encoding means we have to assign. If it is a 3-bit, we can assign from 000 to 111. If you have 2 bits, it is from 00 to 11. If you increase the number of bits, that means if you increase the resolution, for example 4 bits, so it will be from 0, 0, 0 to 1, 1, 1, 1. That means 16 different steps. So there are two ways to improve the accuracy of the analog to digital conversion. How we can improve the accuracy? So one is, we already see that, increasing the resolution. That means, what is the resolution? If you increase the number of bits, it will actually increase in your resolution. So this is the one way to improve the accuracy of the analog to digital conversion. Another thing is increasing the sampling rate, which increases the maximum frequency that can be measured. So sampling frequency, we need to go, fs should be greater than twice of fm. Then it will need higher frequency, the bandwidth will increase. Of course, this is the disadvantage of the digital communication. It requires more bandwidth, but we can have a noise-free signal. Okay. So either by increasing the resolution or by increasing the sampling rate or by doing both, right? So what is this resolution? So resolution means the analog quantization size, right? Number of discrete values the converter can produce equals to analog quantization size or the quantization level. And this quantization level is V range divided by 2 to the power n. That means this is step size. V range divided by quantization level or the whatever we say 2 to the power n. So limited by signal to noise ratio should be around 6 dB. It is the limitation. It is a signal noise ratio is only 6 dB. In our previous example, we saw that Q equals to 1.25, right? Because we have n equals to 2 to the power 3. So a lower resolution will be used to bit converter. Okay. So this is the sampling rate. You can see in the left side we have 1 hertz and the right side we have 2 hertz. So here sampling rate is high, right? So when the sampling rate higher means we are getting more interval, T1, T2, T3. So we can increase the interval as well. Okay, f equals to t equals to 1 over f. So if you increase the frequency, that means you will give it the more close time period. So either you can increase the sampling rate here from 1 hertz to 2 hertz. We can also improve our quality or accuracy. So frequency at which ADC, analog to digital converter, evaluates analog signal. As we can see in the second picture, evaluating the signal more often, more accurately depicts the ADC signal. Or the both, increasing both the sampling rate and the resolution, you can obtain better accuracy in our analog to digital signals. So here, this is the sampling rate is 1 hertz. Here we have 2 hertz. Here the sample quantization level only 4, 0 to 4. That's why resolution is 2.5. Here we have resolution 1.25. So this is how we can increase the power accuracy. Okay. So this is the another graph, same thing. So we can see here, this is the step size we can see, and this is the error rate that we found, 0.5 volt of error rate whenever we have the same example with the 8 steps. Whenever we took the n equals to 3. And we found that our error becomes 0.5, right? 0.5. So this is the error. Which one is the error? For example, here, this is the gap. You can see the gap. This gap is the error. 0.5. This is half. You can see? This is the error. Because whenever they reach here, we are considering as 100. But all these values are actually considering 100. So error maximum will be 0.5. And this is the step size. You can see here, this 1 volt. 1 volt. 1.5 to 2.5. 1 volt is error. So as I mentioned that we have two different kind of what I mentioned. This one quantizer. One is mid-rate and one is mid-rise, right? Or the uniform quantizer. We use mid-rise quantizer, mid-rise uniform quantizer. So in the mid-rise means whenever they will come, they will point of the quantization values, they will rise. 0.5, 1.5, 2.5. When they will come to here, they will rise. That's why it's known as mid-rise. Today I'm finished. Today I have a short lectures. That's it. Do you have any questions for the exam?
Oh, what is the pattern?
Pattern of exam? Okay. Exam will be, so we have from conversion to until what? Marks. Encoder, right? So if I start from the coding system, so we have to focus on Hamming code, how we can do this Hamming code. I will give the example, then you have to generate this Hamming code for that particular information. It can be event parity, I mentioned. You have to choose either event parity or odd parity. Then if I go for the De Morgan's laws or the Boolean's laws, then I will give some expression. You have to simplify those expressions. Then maybe you can design the circuit, logic circuit. Then if I go for this, we already discussed about the SOP, right? And POS. So we also saw that how we can convert from non-canonical to canonical, both for POS and SOP. You can practice those things. And then we'll talk about the full adder circuit, full substitutor circuit, how we can design those full adder and full substitutor circuit. Then we also calculate one propagation delay for particular full adder circuit. So we can do that math, only one math is there. Then we can talk about how we can design a full adder circuit or priority encoder circuit by using a DMUX, by using our encoder. So these are the things I already mentioned. I think I already uploaded.
Yeah, sir. I'm asking about the pattern actually, like how many questions and how many marks? Like what is it? We'll have multiple choice or
No multiple choice. No multiple choice, only this kind of questions. So it will be around 40 marks to 50 marks. And you maybe have to answer around 10 questions.
Do we have choice?
Yeah.
Short answer question.
These are all short, not MCQ, not short answer, everything is short answer. So you will be, for example, there will be 12 questions, you have to answer any 10. Or there will be 10 questions, you have to answer any 8. There will be some, mostly there will be equal number. So, for example, if you have to answer 8, so 8 into 5, 40 marks. If you have to answer 10 into 5, 50 marks. Okay. Actually, I didn't make the question yet. That's why I don't know how many questions will be there. So I will try to make sure that within 1 hour, 15 minutes, so you can answer. So that's why maybe 8 or maybe 10. And I don't think, do you need, someone asked me about the formula sheet. Do you need to provide the formula sheet for those Boolean law?
Not
Boolean's law, there are so many Boolean's laws. So I can get you that formula sheet of the Boolean's law. I don't, other than that, nothing else, right? Only the Boolean's law.
And,
Okay, I will provide that.
And will you provide the answer of the SM1 document?
So which one? Sir?
The SM1 preparation?
Preparation.
Yeah, will you provide the answer of that?
I have.
Okay.
You have the answer in your lecture?
Oh,
From lecture 1 to lecture 8. Right? Each and every question has the answer in my lecture. Each and every.
So basically, I mean, we'll get most of them whatever we have.
Yeah. What we have studied here, you will get the same thing.
Will it be more like, for example, with demultiplexers, will it be analysis of an existing diagram, or will you have to draw or design?
Draw and design. So whatever you want to draw, maybe you can just give a truth table, how you get this, how you get this expression.
like we need to just, there will be a diagram and we need to find the equation for the diagram.
No.
So
For example, you make the logic circuit, then you have to get this expression.
Yeah.
Oh, that can be.
Yeah, it is there in the example preparation.
It can be
document.
also.
There was a logic circuit diagram, then we need to follow the diagram to find the equation. Or you might give the equation, we need to.
Yeah.
Draw the
So
Draw the
I
diagram.
already give the sample, yeah.
Okay.
Very simple. And very easy to my student.
We know.
Anything else?
I have a question regarding this. Yes, we know we do not. We have what called we in your statement that human is very close to. We're calculating it, but how does a digital electronics or a device system understand?
So that's we cannot, in digital communication, they said that we cannot remove the error. There will be error, but we can reduce the error. Because if you want to remove the error, you have to increase the number of bits. But if you keep increasing your number of bits, what will happen? It will increase your bandwidth. For example, after I have one more last slide, you can see here, whenever we have 16 bits, 2 to the power 16 bits, you can see here. So here the discrete state is 65,536.
Yes.
And we have the energy weight as this amount. So that means value of quantization is 153 microvolt. This is enough. But sometimes maybe you have less than that. So here the signal to noise ratio is almost 107. So there is no error actually. So but for that case you have to have 2 to the power 16 bits. So it's a bandwidth will increase. Your bandwidth will increase. So this is the digital communication. You can get a noise-free signal, but with the cost of bandwidth.
Performance against the time, all the time.
It depends which one you want to focus.
Yes.
For example, there are product from Europe, there is product from China.
Yes.
If you want for quality, you go for Europe, but you have to pay. iPhone versus there is some phone that people from here they don't know. In our country we have
Yes,
that
yeah.
Oppo, Xiaomi, they never heard about these things.
Yeah.
You can buy only $100 phone, right?
Yeah.
Even $100 you get phone. But here it's not possible. So this is about quality and price. See? Yeah.
The second line, avoided alias error. Yeah, avoided alias error.
Alias error means wherever there is, yeah. Did you solve that question also? You are